Okay, let's enjoy some puzzle solving with the Y gate. And yeah, from the first puzzle, we don't have a Y gate, but that's not a problem. We have one already placed for us. And how do we get rid of it? Well, first let's get rid of the color. Yeah, and then we know the trick. We've done it before, which means we should be able to create the next gate without an actual X gate. Yeah. Okay, for the second puzzle, we have here two H gates. They do absolutely nothing. It's kind of to make a point. They really don't do anything because they annihilate each other. Yeah, quantum gates are reversible, so keep that in mind. But we do want this green. How can we pick up the green? Well, if we just add an X gate, we'll get our green, right? But we would need to reverse it, and there's no way to reverse it, right? So we need to somehow not even use that. And that's the trick. That's what the puzzle tries to teach, is that we cannot use these. We need to do something more mysterious by, you just add the Y gate for the first time here, and then you should be able to solve it quite easily. Now, this is your standard, how do you make everything green? So quantum state, which is just I. And yeah, you need to annihilate the minus from the minus i's that were here with adding another Z gate. Okay, now, we want to be in the one state, but we have three S gates. And these two H gates don't really do anything for us because we don't want any type of superposition happening. So let's just kill them. And if we add an X gate here, then, oh boy, then we're gonna have a gold state. But what if we add a Y gate, right? Because then gold with green will become blue. So that's a solution. Another solution would be to, of course, do this, right? And as you know, 4S gates rotate back to blue. Okay, on puzzle 6, what do we have? So that's a complicated looking split, but does it really have to be complicated? Because if we just analyze the algorithm, there are these Y gates here, but we don't want to mess with the Y gates, right? So let's just destroy all the colors. Again, green, gold, green, gold, green, gold, make blue. Everything is blue and nice. And that's it. We have the solution. All right, now we got gold and we have two forced H gates. This could be tricky, but it doesn't have to, right? Because we have the Y gate and we know that we can flip by adding a color, right? So the same thing as if this would be Z. Yeah, we flip without color. The Y gate does that basically. Not the S. The S creates the yin yangs, right? So you can just use the Y gate to get your color out, like the way I just did here. Gold plate, nice. How do we get the gold plate? I think the best and most efficient way would be to do this, make this gold before, add H's, and then kill the reds, right? So this becomes gold, this becomes green, green, going through red, they become all gold. That's the solution. Okay, now in this situation, Y gates everywhere, that's nice. But is it really nice? Because on qubit 4, we want to have a superposition instead, right? And we are entering with red. So if I were to just add the H gate here and observe, we get red, blue, and we want to have gold, gold. So how do we fix it? Let's just do this, right? Adding another color, and now we have green, green. And I want this green to become gold. But if I add a green here, if I add a Z here, only the rightmost will become gold and the leftmost will not. Why? That's because this is in the 0 state and the 1 state at the same time. So only the one in the 1 state on the qubit 4, the rightmost qubit, will pick up the red color. The other one will not, and that sucks, right? So this means I have to place a Z gate anywhere else. And if I place the Z gate anywhere else, then I get both gold. And I think now you start to understand why, right? Because you see, in all cases, the qubit is on, it will be getting both colors. So even if I place it here, I get my gold gold. If I place it here, anywhere except in this quadrant or here, yeah, I will get my solution. So for the last puzzle, wow, this looks tricky, right? Because we want to have a superposition, and we want to have it on qubit 1. Yeah, because this is 0 and 1 at the same time. We want to have another one on qubit 3, definitely not on qubit 2. Why not on qubit 2? Because if you look at what's highlighting here, qubit 2 is always in the 1 state. So we definitely don't want to add a H gate on it, right? But also we want to have on qubit 4 because qubit 4 is in the 0 and 1 state at the same time. So wow, now we have all greens and we want to have them become red. But if I add here gates, I don't think this is gonna work because there is no way to transform everything to red, because some qubits are 0, some qubits are 1. So if I were to just add greens everywhere, this is not gonna work under any circumstance. And I think that's really annoying for you guys trying to solve this puzzle. But yeah, this is a fundamental rule that's trying to be shown here. And if you don't know it, you have to discover it. That's how puzzle solving works. You have to discover these rules on your own. So what I might need to do, what if I move this position here? Because it doesn't matter, it's commutative. And I can just add this Y on qubit 1. And greens with golds will destroy it, because just watch. So green will go through 0, and that will make it red. Gold will go through gold, and that will make it red. So adding a single Y gate here, that's exactly what we needed. And that's how you solve the puzzle. And I hope it's clear. Yeah, again, let's watch that one more time. The 0 will go through green. Yeah, from 0 makes 1 through green, and that's gonna make it red. And the other way around, gold with gold will make red.